Okay. All right, guys. Welcome back to week 11 of the interactive sessions of the course Viscous Fluid Flow. So, in the last class, if you remember, we looked into some, you know, sample problems of boundary layer analysis where we use something which is known as the momentum integral approach. Uh, if if you recollect, we use something which is known as the momentum integral approach to, you know, estimate how the boundary layer thickness delta grows or increases as a function of x. Given that we knew a velocity profile of this form, and we saw that if the velocity profile was given in terms of some constants, we are to use the boundary conditions that are available at our disposal, that is at the bottom of the plate and at the edge of the boundary layer, to evaluate those constants, and then subsequently use the momentum integral approach to estimate the value of delta as a function of x. But nevertheless, if we were given a velocity profile already without any unknown constants in it, we directly use the momentum integral approach to evaluate delta. And eventually we saw that delta by x came out to be 4.80 by square root of Rex, which indeed was close to the Blasius's exact result. And then we looked into something which is known as the displacement thickness. We looked into the definition of displacement thickness and subsequently calculated the other quantities like the drag force and you know the drag force to be precise. And then we also saw that the drag force also happened to be the estimated drag force using this approach also came very close to the measured to the results of Blasius's exact solution. Then we looked into a slightly different problem where we were asked to evaluate the characteristic stream function that was used in obtaining the solution or obtaining the Blasius's ODE. And we saw that this characteristic stream function was obtained if we choose the correct scales for the length scale in the x directions, for instance, and the y directions, and subsequently getting the scales for the corresponding velocities in the x and y direction, and using the x momentum equation, writing it in terms of the stream function, and then doing a order of magnitude analysis as we always do to estimate what would psi c be, which is the characteristic stream function that we were asked to evaluate. And we saw that the psi c, the characteristic stream function, came as the kinematic viscosity times the far field velocity times its length with a power of half over it, basically. So this was the value of the characteristic stream function, or in fact, this is the characteristic stream function that we need to choose in order to derive the non-dimensional governing equations pertinent to the Blasius's exact solution. We didn't do the analysis thereafter, but the idea is that if you remember, this was done in the class. So the idea is that you need now to use a similarity variable and then obtain ODE, which basically define how that variable essentially evolved, and then you basically get the solution for Blasius's analysis. Okay. Then we looked into a very simple problem involving some practical values, and then we ended this discussion by looking into something which is known as flow separation. And we argued that this flow separation is a phenomenon that we didn't see in case of flat plate analysis, typically because in case of flat plate, your u infinity is a constant, and if we apply the boundary layer equation after the viscous region, that is above the viscous region, we saw that basically the Euler's equation governed the equation or governs the dynamics in the inviscid region. And we saw that if we apply the Euler's equation, you will eventually see that since your u infinity is not a function of x, you will see that your dp dx is basically equals to 0. Okay, and from the simplified y momentum equation, when applied for a boundary layer analysis, states that your dp dy is also equal to 0, which now means there is the only possibility that your pressure has to be equal to constant in case of a flat plate analysis. That is, it is not a function of y, it is also not a function of x. Okay, but we looked into a scenario where there might be a curvature of the plate, and then it may so happen that locally, if you choose, so what we did is we choose an axis that was locally varying along the curvature of the plate, and then we saw that your u infinity indeed now becomes a function of x. Now if you do the same analysis above the viscous region, that is in the inviscid region, you will eventually see that your dpdx is actually a function of u infinity, which is now a function of x, meaning that now dpdx is not equal to 0. So if dpdx is not equal to 0, we have two scenarios, okay? dpdx can either be greater than 0 or less than 0. So we call the scenario where dpdx is greater than 0 as an adverse pressure gradient, meaning that your pressure is basically trying to tire up the flow, and this was the condition which was a necessary condition for something which is known as flow separation. So we looked into the condition for flow separation in depth, and we also argued that the sufficient condition for flow separation to arise or to take place is that the velocity profile must have an inflection point. For instance, if I have a velocity profile like this profile indicates that there is an inflection point, okay? Because the nature of the curve changes, and the curvature itself attains a local maxima or a local minima, okay? That's the mathematical reason behind having an inflection point. But it's like you can say that the shape of the velocity profile, when the shape of the velocity profile, or when the curvature of the velocity profile changes its sign, it indicates that there is an inflection point, and the necessary and the sufficient condition for flow separation to take place in case of these kind of geometries is that the velocity profile must have an inflection point, okay? So we discussed this in details, and I said that we will end this discussion by looking into something which is known as the Faulkner scan wave flows. And we, of course, you have derived. So just like Blasius's solution was done for flat plate analysis, a similar analysis was done by Faulkner and Scan. And then they, as a special case where this wedge angle, where this beta is known as the wedge angle of a wedge of the given wedge. And where this beta tends to 0, you get the exact Blasius's ODE that we saw. So it's like the Faulkner scan solution are kind of a general solution for any arbitrary geometries, and as a special case where beta, that is the wedge angle, is basically equal to 0, gives you the Blasius's solution for flat plate analysis. Okay, so what we will do is we will not exactly solve for we'll not go into the details of the solution of how to solve this Faulkner scan solution, but we will give you an idea that flow separation indeed takes place in case of geometries where this beta is essentially equal to non-zero. Okay, and this argument we will put forward by doing a similar analysis that we did for the case of that we did for this example, where we looked into flow separation by applying Euler's equation in the inviscid region. Okay, so we'll do a similar analysis on this, and we will see that we will indeed prove that if beta is not equal to 0, then indeed indeed the fluid can have flow separation, or I mean the fluid can what to say. So basically, the fluid can separate from the solid surface. Okay, is the criteria that we will look in this analysis. But we'll stop here for a couple of minutes as a ritual that we all do. And if you have any question, you can ask, and or we'll begin in 1 or 2 minutes. So this is where we stopped it in the last class. We'll discuss this Faulkner scan wave flows, and then we'll start a new topic today that is known as hydrodynamic stability or hydrodynamic instability, and we will see what we can do in that. So that's a completely new spectrum or a new ball game, and we will see what we will do there. But before that, I would like to finish this Faulkner scan wedge flows, and give you some idea about flow separation taking place in these kind of geometries. Okay, so as we did for this, for this curve plate, in this, so what happens is there is a solid surface which is in the form of a wedge. So these kind of surfaces are known as wedge surfaces, and this inclination angle of one surface to each another, it is given by beta. You might take beta to be equal to so it's up to you on what you might, for instance, you might take beta to be equal to pi by 2, then it becomes something like this. Okay, and it's up to you on how you choose basically the value of beta. But a non-zero beta, as you can appreciate, ensures that there is, so for instance, if my beta is non-zero, then of course there is a finite inclination of one plate with respect to the other. And as I said, we will see that this inclination is what ensures that dpdx is not equal to 0. Okay, so what we will do is, our objective is to basically prove that dpdx is not equal to our objective is to prove that the pressure gradient is not equal to 0, okay, when beta is not equal to 0 basically. Okay, and we will see how we go on with this. Okay, so at first what I do is I apply, so So I apply the Euler's equation in the inviscid region. So recall that we take the axis. So we take the x-axis, which is parallel to this plate, and the y-axis is basically perpendicular to this plate. That's how we take the axis here. It's similar to the one that we took for these kind of geometries. Uh, so if we apply Euler's equation in the inviscid region, okay. So what do we get? So the Euler's equation gives us what? It says that v dot grad v is equal to minus gradient of p. But since the flow is taking place, let's say in the x direction, which is obviously the case because this is the flow, this is how the flow is coming in, and then when it suddenly sees this plate, it will try to move in this particular direction. So we are writing the flow. So the dominant direction in which the flow is taking place is indeed the x direction. So if I write the x component of this equation, it will just, you know, you will just get to be rho times u infinity. Of course, there is a rho here. That is rho times u infinity x, gradient of u infinity. So since u infinity is just a function of x, so v dot grad v, this term, that is this term, would simply boils down to be u infinity x times d of u infinity by dx, because of the fact that my u infinity is just a function of x. And yeah, I forgot to mention one thing, that so what we do is we take a specific form of u infinity, which is of the form c times x to the power m, and this m is nothing but just a parameter which is related to the wedge angle. Okay. Now you can ask me, or you can say that when m is equal to 0, meaning that my beta is equal to 0, this gives you that x power 0 is equal to 1, which means that your u infinity is just a constant, and this is the case for a flat plate analysis. Okay. So as a special case for m equal to 0 is the case where we get the flat plate. Okay. Now you can ask me that what is the basis of choosing this u infinity in this form. Okay. That why do I choose that why do we choose u infinity of in this kind of manner? Now this answer, so the answer to this actually comes from something which is known as the so the answer to this actually comes from something which is known as the potential flow theory. But you can you so I'll not go into the nuances of how does u infinity basically is taken something like this. Rather, I would suggest you to read the textbook prescribed, and there is beautifully in those books it's beautifully written that why u infinity is of this particular form. But I'll give you a hint that this comes from the potential flow theory, number one, and number two is that these kind of velocity profiles are easier to analyze. It's kind of an so what is this kind? It's kind of a polynomial profile, okay? And you get you get a plethora of information if you consider velocity profiles of these kind of forms, okay? So that's the reason. I mean, that's a crude reason of why u infinity is chosen to be of this form and not of any other functions, okay? Uh, that is something that I can say as of now. Okay, all right. So when we are since we already know u infinity, we can substitute it here. But first, let's write the right hand side. So the right hand side would just become minus of dp by dx. And since we know that u infinity is c times x to the power m, this means that du infinity by dx is equal to what? It will be equal to cm x to the power m minus 1. Okay, which means if I substitute this, then I get my dp dx. That means I am writing this equation here. So I get dp dx as equal to minus rho u infinity was c x to the power m, du infinity by dx was c m x to the power m minus 1. So this means that I get dp dx as what? So I get it as rho times c square x to the power m. Okay, that's it. So that's the pressure gradient that we get. Okay. Sorry, I think I did a mistake. I think, sorry, this has to be rho c square x to the power twice m minus 1. Very sorry. Just x to the power twice m minus 1. Why? Because this is because of the fact that, you know, when So this is m minus 1 and this is m. So this become x to the power twice m minus 1. Okay. So this is what your dp dx would look like when we just apply the Euler's equation in this case. Okay. So now if I apply the x momentum equation, if I apply the x momentum equation inside the boundary layer, okay, then what do we get? So we get, so it's like, so what is this equation inside the boundary layer? So it is u del u by del x plus v del u by del y. These two terms are there. And then this becomes, and of course there is a, so what? Okay, so you can write a rho here. Okay, and then this becomes minus of dp by dx because of the fact that your pressure gradient is just a function of x. Since if you apply this to the y momentum equation, you will simply get that I mean del p by del y is equal to 0, which means that your pressure is just a function of x, and that's the reason why I wrote it here as dp by dx and not del p by del x. And I hope you can appreciate this. And then I have plus of what? Okay, and then I have plus of mu del square u by del y square. Okay, but from the Euler's equation I know that dp by dx is of this form. Okay, so this becomes rho times u del u by del x plus v del u by del y, and then this is, so dp dx is minus of this, so this becomes rho c square, rho times c square x to the power twice m minus 1. Okay, I think there is also an m here. Yeah, so I forgot to write an m. There is also an m here. You should not forget this. So there is an m multiplied here. Sorry for that. Yeah, that is simply because if you take the case for m equal to 0, this is the flat plate. You get this term to be equal to 0, and you get dp dx equal to 0, which is the case of a flat plate. I just forgot to wrote this m in this in this step. All right. So there is an m here. And then I have plus of mu times del square u by del y square. So if you just simplify this equation by dividing it by rho, you will just get u times del u by del x plus v times del u by del y. And then this becomes what? This becomes c square m x to the power twice m minus 1 plus mu del square u by del y square. So this is how your x momentum equation, can be written in case of wedge flows, or in case of flow over wedges. Okay, but the good thing is you can appreciate that your dp dx, which you evaluated by using the Euler's equation in the inviscid region, you saw that it came as minus rho times c square m times x to the power twice m minus 1, which means that if, as I already said, if m equals to 0, then it just directly, gives us the fact that dp dx is equal to 0, which means this is the case for a flat plate, analysis. Okay, and if m is, see, this x this x is basically the length of the plate. Okay, this x can never be negative, which means that this quantity is always greater than 0, because of the fact that even if 2m minus 1 is less than 0, this means that my m is less than equal to half. Okay, then this term will become as a fraction, but it can never be negative because of the fact that my x is always greater than 0, which means it is only the sign of m that decides whether that this dp dx is going to be greater than 0 or dp dx is going to be less than 0. So it is that m which decides. So for instance, if so what I was saying, that this term is positive, these two terms are positive, which means that if my m is greater than 0, this means that this term is greater than 0. So dp dx, since there is a minus sign here, this would be less than 0. Okay, so if m is greater than 0, then I have dp dx less than 0, and this is the case for a favorable pressure gradient as we already saw it in the last class. Okay, this is the case for a favorable pressure gradient. Similarly, the third case is that if m is less than 0, meaning that my dp dx will now be greater than 0, and this is the case for an adverse pressure gradient. Okay, this is the case for an adverse pressure gradient. Okay, where recall that your m, so your beta, so see your m is which comes in the flow profile, this is related to the wedge angle as something like this, and this again comes from the potential flow theory. So your beta, so once you know m, you basically know that your beta is nothing but twice m by, you know, your beta is nothing but what, twice m by 1 plus m basically. So once you know m, you kind of, so once this m is known, you kind of know beta, and once you know m, you also know how this pressure gradient is basically going to behave. Okay, whether this is going to be an adverse pressure gradient or this is going to be a favorable pressure gradient. For example, see this scenario. So I took two examples. Okay, one is the flow around an expansion corner, meaning that there is now a wedge which is of this form, and this is the direction in which the flow is coming place. And now there is another in and in another case, I have a pure wedge flow where, you know, beta is basically less than where beta lies in between this range. Okay, now you can appreciate that whenever there is an expansion corner, okay, since beta is basically negative, if beta is negative, then m also happens to be negative. Okay, which means that I have an adverse pressure gradient according to the results that we describe, and that's the reason why my dp dx is greater than 0, meaning that if there is a flow taking place around an expansion corner, it is there is an adverse pressure gradient that develops, and if the flow cannot sustain by itself due to its inertia, there will be separation. Okay, so expansion is, so flow around expansion corners are liable for separations, but flow over wedges are, you know, there, so flow separation is not possible there because of the fact that in case of wedges, your beta lies in this range, meaning that your m is less than 0. Okay, which means, sorry, your m is greater than 0, that's the other way around I said, which means that your dp dx is less than 0. So in expansion corners, okay, in expansion corners there, so as I said that once you don't know whether there will be an inflection point or not, you do you cannot, you know, you cannot, what to say, so that's, so you don't have a strong or you can say you don't have a sufficient condition to justify that there will be flow separation. But if you can ensure somehow that the pressure gradient is greater than 0, you can say that if the flow cannot sustain by itself, you know, it may so happen that the flow can separate. Okay, so the bottom line is that in case of expansion corners, you can have flow separation. Okay, on the other hand, whenever there is a flow taking place, you know, whenever there is a flow that is taking place around the conventional wedge where your beta lies in this range, your dp dx is less than 0, meaning that your flow cannot separate. Okay, there is no possibility of flow separation. Okay, there is no possibility of flow separation. And this is again obvious because if your dpdx is less than 0, pressure is essentially assisting in the direction of flow, meaning that inertia and pressure are assisting each other, and that's why it will keep the fluid, you know, keep the fluid adhere to the surface of the plate, and they will move basically along. They will kind of like glide along the surface of the plate without essentially the flow getting tired up and leaving the surface of the plate. Okay, so that's the idea behind the fact that what happens if your dpdx is less than 0 or your dpdx is greater than 0. So the bottom line is that what you need to see is you need to have a knowledge of the velocity profile. From the knowledge of the velocity profile, use the velocity profile to in the Euler's equation, uh, where you apply the, so basically you need to use the velocity profile and then apply Euler's equation in the inviscid region, which is outside the boundary layer, and then see what is your dp dx, because you know that since your pressure is not a function of y, your dp dx in the inviscid region is the same dp dx that you will get in the boundary layer. Okay, and then you can substitute the same form of dp dx, which will give you the boundary layer equations for at least the x momentum boundary layer equation for flow taking place in case of geometries, for instance, like these wedges or expansion corners. And then the sign of your dpdx dictates if there is a flow separation that will take place or not in these kind of geometries. Okay, so that's all. That's the idea behind this Faulkner scan. So we didn't look into the solution of the Faulkner scans with Faulkner scan solution, but I can assure you that the solution, the methodology for this solution is exactly the same that we do for Glacius's analysis, where again you need to use the similarity variable. The only difference is that now your u infinity becomes a function of x, and in fact it is taken to be of the functional form c times x to the power m. Okay, yeah. So that's pretty much with boundary layer analysis, and this finishes boundary layer analysis uh, I mean in the discussions that we are having. And now, without any delay, we will move into a new topic which is known as hydrodynamic instabilities. Okay, and we will, so there are many hydrodynamic instabilities. I will in the next 1 or 2 minutes I will give you I will give you some motivation on why do you need to study hydrodynamic instabilities. But and as I said that there are many forms of instabilities in fluid flows. I'll give you some examples of those forms. But as an exercise, what we'll do is we will try to assess the stability of something which is known as inviscid parallel flows. So we'll try to assess something which is known as the stability of inviscid parallel flows in details, and then derive something which is known as the Rayleigh stability equation, which govern actually how the disturbance stream function basically. So the Rayleigh stability equation gives us the stability criteria for inviscid parallel flows, and as we will see later that the stability criteria comes in form of the eigenfunction of the stream function that of the stream function normal mode that we consider, and it gives us how the eigenfunction basically varies with varies given that we have an eigenvalue c that we will see later on. But in short, it gives us whether a given inviscid parallel flow or a nearly inviscid parallel flow is stable or not, is what is determined by this Rayleigh stability equation. And once, so as of today we will see this. I don't think so we can finish this because it's kind of a long exercise that we'll do, and we'll proceed very slowly given that we are doing it for the first time. But once we are done with this, once we are done deriving this Rayleigh stability equation, I'll give you certain insights of this Rayleigh stability equation, and then we'll look into some stability criteria that can be used, uh, which can be used by using the basis of this Rayleigh stability equation, which are known as, so for instance, one of those criteria are known as Rayleigh inflection point criteria, and a stronger criteria to this Rayleigh inflection point criteria is the Jortov's criteria. And finally we also have another criteria which is known as the Howard semicircle theorem. And these are the things, these are stability criteria which uses the Rayleigh stability equation to determine whether a given base flow, so we'll see what a base flow is, but it says that if we have a base flow, adding perturbations to this base flow, does adding perturbations to this base flow makes the base flow unstable, or it leads to stability. So these are the things that we will see. And yeah, that's the next. So this is the roadmap for the next for this for the remaining of this class and the next class. And then maybe we'll try to have one more extra class where I will show you how to solve an eigenfunction, because you will see that inevitably linear stability analysis leads to eigenvalue problem. So we will also we'll see. So at least we have, so at least where so in the class you derive something which is known as the Orr-Sommerfeld equation, which is again an eigenvalue problem. Okay, so we will prove that, or we will see, we cannot prove, but we will see also from this example that inevitably linear stability analysis gives you an eigenvalue problem. So it also becomes essential for us to learn how to solve eigenvalue problem. For instance, if someone asks you how to solve this Rayleigh stability equation, this is an eigenvalue problem essentially. Okay, and we'll look into some standard procedures for solving eigenvalue problem of these kind of forms. Okay. All right, so this is the agenda for the next classes, and I'll stop here for a couple of minutes. If you have any questions, you can ask, or else we'll begin with this new chapter of hydrodynamic instabilities. Okay. Okay, all right. So before going into the math and going into the analysis of these stabilities of inviscid parallel flows, let's quickly brush up why do we need to perform a stability analysis. So it's so let's say there is a flow that is taking place through a pipe, okay, and you are you so basically you want to transfer the fluid from let's say a station A to a station B, which is located at, I mean, the difference between these two stations are few meters or few kilometers. That depends upon the utility of, or that depends upon exactly where you want to send the fluid. But the idea is that, so how this is typically done in practical sense is that if you want to, let's say, pump a fluid, or if you want to send the fluid, or basically pump a fluid from a station A to a station B, then what you need to know is actually some physical quantities like the diameter of the pipe, I mean, things like friction factor and all those things. And you also need to know the pumping power which you would at least require to overcome the frictional losses such that you can send the fluid from point A to point B. Now, the pumping power is highly a function of what is the Reynolds number of the flow. Okay, for instance, if your flow is turbulent, then your pumping power would be different because there will be eddies that will be formed and all those things will take place. We'll not go into turbulence as of now. But if you're on the other hand, if your flow is laminar, then you will have a different pumping power. Okay, so for the given fluid and for the given dimensions of the pipe, it is the nature of the flow that also dictates how much power you would require to send the fluid from point A to point B. Now, if you a priori don't know that is your flow laminar or is your flow turbulent, then ultimately you don't know what is the pumping power. Okay, now this laminar to turbulent transition, that whether if you send a fluid from point A to point B, the flow will remain laminar, or if you send a fluid from point, or the in the meanwhile, when the fluid is moving from point A to point B, there could be a region, let's say C, where the flow transition from laminar to turbulence. All these things, these transition zones and all these things are governed by instabilities in the fluids. Okay. For instance, if there are instabilities, for instance, there is a laminar flow that is taking place, and because of certain disturbances or because of certain regions, there is an instability that kicks in the fluid. Now, these instabilities can make the flow can these instabilities can grow with time, which will make the flow transition from laminar to turbulent, let's say. Or these instabilities, if there are any, this may decay with time, meaning that even if there are instabilities, it will not make the flow unstable, kind of like this. Okay, the instabilities will kind of decay the instabilities will decay. So it is so it now becomes use so it now becomes important to see what will be the nature of the flow, is to study how these instabilities basically behave. Okay, and that's the reason why in practical sense we need to study hydrodynamic instabilities. Okay, so I hope I could establish a motivation for studying this very very important aspect of fluid dynamics, which is known as stability analysis of which is known as stability analysis of fluids, or people call it as hydrodynamic stabilities or instabilities. Okay, and there are many examples of hydrodynamic instabilities. For instance, the gravity waves that you see on ocean, this is an instability. If you, for instance, there is a container, and if you heat the container, the fluid which is below the container, it gets warm, meaning that it gets lighter, and the fluid which is above, which is cold, it is heavier, and this drives the circulation of the lighter fluid to the heavier fluid, and this is famously known as the Rayleigh-Benard instability. Okay, on the other hand, there is another example where you open a tap. Let's say you open the tap of your kitchen sink. You will see that initially there is a jet of fluid that is coming, and then after a certain distance, this jet of fluid breaks down into drops. This phenomenon is not so this phenomenon is not solely driven by, in fact, this you might have thought that okay, there is gravity, so that's the reason why there is breakdown of this jet. But gravity is not the main reason why this breakdown of jets causes in case of, let's say, fluids coming out in the form of jets. In fact, you can show that if there is no gravity, then also these jets will break down, and these kind of instabilities are driven by surface tension, and they are known as capillary instabilities, or they are known as Rayleigh-Plateau instabilities. Okay, that's so this is the classic example where surface tension actually makes the flow unstable, because you I'll so we will not have time to study Rayleigh-Plateau instabilities or capillary instabilities. But what happens is, whenever so what happens is, when the jet comes down, surface tension basically deforms the interface. Okay, that's the reason why there will be regions, there will be pockets where pressure will be higher, and there will be regions where pressure will be lower. So so along the stream, the difference in pressure is what causes the jet to break down and form droplets, and this is typically driven by surface tension. On the other hand, there is another form of instability which is known as Kelvin-Helmholtz instability, and we will, at the end of this discussion, I'll give you a brief idea. Although we'll not do the math, I'll give you a brief idea of what Kelvin-Helmholtz instability is. Okay, with and this instability happens whenever there is a relative motion of two fluids that is taking place. For instance, if there is a pipe and there are two fluids which are sitting atop one another, and when there is a relative motion of one fluid with respect to one another, it causes an instability which is basically known as Kelvin-Helmholtz instability. And in that case, surface tension actually stabilizes the interface. Okay, so these are some classic examples of instabilities in multi-phase flows. But we will not see multi-phase flows as of now, because that becomes a little complex in terms of the boundary condition. But in the same time, we'll look into a very simple and a very similar, a very simple case, which is the stability analysis of inviscid parallel flows. Okay, the stability analysis of viscous parallel flows you have already saw in the lecture classes. What we will do is, we will do the analysis in case where the flow is inviscid, and eventually we will we will establish an equation which governs its stability. This is known as the Rayleigh stability equation. Okay, so that is the idea that we will do, and I hope you have appreciated the different examples of stability, or the different examples of hydrodynamic instabilities that can take place in various flows. And these are classic examples, and there are very nice papers written on it. For instance, remember we solved a problem related to the Taylor-Kuet flows. There are also instabilities that are related to these kind of flows. Okay, that is known as instabilities in Taylor-Kuet flows, and you can show that Taylor-Kuet flows are essentially unstable. That you can also prove. Okay, so these are kind of examples that are there in hydrodynamic instabilities. There is a very good book known as Dresden and Reed. I think the name of the book is Introduction to Hydrodynamic Instabilities, and the authors are Dresden and Reed. The publisher is Cambridge University Press, and you can read this book if you want to learn more on hydrodynamic instabilities. Okay, but having said that, let's start with our I hope I have given you enough motivation so as to why we need to learn stability. Now, without any delays, let's start our first problem, and in fact we'll just solve only this problem, because stability problems are very large. And in fact, you will see that we will this problem that we'll solve, although it seems to be very simple, you will see that it is indeed the algebra is indeed very cumbersome, and it takes time to digest done, or it takes time to understand the essential features of stability problems, and that's why we'll proceed very slowly. But at the same time, we will keep in mind that whenever we go ahead with this analysis, we will we will see certain very interesting aspects of various cases uh, at at uh, at uh, at certain instances of the analysis that we'll do. Okay. All right. So I'll stop here for a couple of minutes, and then we will start off with this instability of stability of inviscid parallel flows. In the meantime, I'll just come in 2 minutes. I'll just fill my mug with some water. Okay, sorry for the interruption. So let's start uh, with with our analysis. So what we have is we have two parallel plates of this form, and then we have something which is known as a base flow, which is which is uh, which is an arbitrary flow that is taking place in the x direction. Okay, and it has variations along z. So the reason why this is known as base flow is that all the properties of this flow is known to us. Okay, the velocity profile is known, pressure and properties like the fluid properties, the velocity profile, pressure, everything is known to us. Okay, so this, so the quantities that are known, these are known as base flow properties. For instance, we know the base velocity profile, we know the pressure. Okay, the idea is that once we know a given base flow, if there are perturbations to this base flow, then the the question that we seek to answer is that will these perturbations grow with time, or will these perturbations decay with time, which will make the flow unstable. I mean, which will make the flow prone to instabilities, or eventually the perturbations will die down and the flow will become stable. Okay, so that's the question that we seek. And before formally trying to establish the problem, there are some bookkeeping stuffs that we need to understand. So in this analysis, all the quantities that are dimensional, we'll consider it as starred. For instance, this U star denote the dimensional base flow, Z star denote the dimensional Z direction, and similarly X star and Y star. PB star denotes the dimensional, base pressure, and yeah. And the second thing is that we will do something which is known as a linear stability analysis. And the consequence of linear stability analysis is that my perturbations, which we will denote as uh, yeah. So before like trying to understand the condition for linear stability analysis, let's look at the notations of the various variables. Okay, so the aggregate variables, we call this as the total variable, which comprises of the base variable and the perturbations. We will denote it as we will denote it as small letters. The base variables we will denote it as uppercase letters, and the perturbations we will denote as dash quantities. Okay, where the star, we are writing the star because this is showing the dimensional quantities. The corresponding non-dimensional quantities will be A, capital A, and A dash. This A will denote the aggregate variable, capital A will denote the base variable, and A dash will denote your perturbations. Okay, and in this case, and also in the cases where you saw in the which you saw in the theory classes, we will do something which is known as the linear stability analysis, and this means that your perturbations, which we denote it as dash quantities, the magnitude of these perturbations are very much less than the magnitude of the base flow, meaning that if you take a ratio of V dash by capital V, this is very much less than 1. And this is the domain in which the linear perturbation analysis works, and we will stick to this domain where the perturbations, if they are present in the fluid, their magnitudes, these are very much less than the magnitude of the base flow. Okay, and this is the condition for linear stability analysis, and we will stick to these conditions in the subsequent algebra that we will do. Okay, all right. So I hope this bookkeeping stuff is clear, that your star is a dimensional quantities. Your will denote the base flow by capital letters, will denote the aggregate variables by small letters, and a dash in the small letter will give you the perturbations. And we are in the regime of linear stability analysis, which means that the magnitude of your perturbations are less than the magnitude of the base flow. Okay, so we will begin this analysis. See, the objective is that if there are perturbations, we want to see that whether these perturbations grow with time or these perturbations decay with time. Now this growth rate and the decay rate is dictated by something which is known as the eigenvalue, and we will see that what eventually is the eigenvalue that will come out or that will pop out in this analysis. But before that, at least this is the objective that we want to address in this problem, and I hope it is clear to you what we are actually trying to do in this analysis. Okay, all right. So let's start off by writing the assumptions of this problem. So the assumptions are that the first is already written in the problem, that we are considering an inviscid fluid. The fluid is inviscid, and also it is incompressible. Okay, The second assumption is that your base flow is unidirectional. And this is of course the case because your base flow, which is u, this is just a function of z. Sorry, this is a function of z, but it has a direction in the x direction, which means that although your base flow is varying along the z axis, its direction is only in the x direction, which means that your base flow is unidirectional. Okay, so we are considering an unidirectional base flow. And the third assumption is that your base flow is steady. Okay, so these are the three assumptions that we will consider. All right, now there are certain steps, there are certain standard steps that we need to follow in order to carry out this linear stability analysis. So the first step that that I think you guys have already saw is that we will start off with the governing equations for the aggregate flow field. Okay, so governing equation for total variables, total variables. Okay, this is the first step. And of course, this is the first step of any flow problems that we do, that we write the assumptions and then we write the governing equations. Okay, so then what are the governing equations? So the first equation is, as we all know, that's the continuity equation. And the continuity equation would just be divergence of, so this is divergence star because it's a dimensional quantity. It will be del star of v star is equals to 0. That's the continuity equation. And the second equation is nothing but the Euler's equation because of the fact that your flow is inviscid. So we have the Euler's equation which governs the conservation of momentum. So it is just del v star by del t plus v star dot grad v star, and this is also star, and this is equal to minus gradient star of p star. Okay, that's the Euler's equation. And we'll name this, let's name the equations because we will have numerous equations coming up in this analysis. So let's name this equation. Okay, where recollect that this v star, that is v star, is the total velocity field, because remember any that lowercase variables are the aggregate variables, variables which comprise of the base variable and the perturbations. So v star is nothing but your u star times ex, where your u star is a function of z that we already saw, and this also comprises of the perturbations which are v star dash. Okay, and your p star is basically your base pressure, which is capital P star, plus P star prime, which is your perturbations to the pressure. Now this aggregate variable, v star, this is a function of what? This is a function of x bar star, that is uh, the position vector and also time. Okay, your base flow is not a so the knowledge of the base flow is known. You know that your capital U star, this is just a function of z, because this is given in the problem. This is just a function of j star. Okay, but your v star dash, that is the perturbation, they are also the function of all the that is they are functions of the position vector x star bar, which so this x star bar is nothing but x star ex hat plus y star ey hat plus z star ez hat. Okay, so your perturbation, see, although your base flow is unidirectional, but this doesn't say that your perturbations are unidirectional. Your perturbations can be arbitrary because you don't know how your perturbations are going to propagate and in which direction your perturbations are going to propagate, and that's the reason why your perturbations are essentially a function of the total position vector, that is x star, y star, and z star, or we call it as x bar star. And also there, you don't know that your perturbations are going to be steady or not. So in general, your perturbations are And it is the time dependency of the perturbations which makes the, you know, I mean, your perturbation has to be a function of time, okay, because this indeed say, I mean, this is the reason how you can say that your flow is stable or unstable. It's so because your perturbation should essentially vary with time, okay, which means that my p star dash is also a function of x star and t, and this makes the aggregate variable p star also a function of x star and t. I hope you can you can appreciate how did we basically write these steps, okay, and how these dependencies are established in this problem. We will name these two equations as, let's say, equation what, 3a and 3b, okay. Now the good thing is you can show that your base variable, so these two are the base variables, these two are the base variables, and you can show that your base variable trivially satisfies the governing equation, meaning that your base variable trivially satisfies these governing equations. How? That is something that we will see, okay. So what I propose is that so these variables, that is these base variables, trivially satisfy the governing equation, okay. So how is that? Let's start off by writing the continuity. So the continuity equation, when you write for the base variable, will, so this will just boil down to the fact that del u star, which is a function of z. So remember this capital U, so this u is the capital U and that is the base variable. We are writing equations so we are writing the governing equations that the base variable satisfies, okay. So this is going to be del u by del x. This is the continuity equation. This is going to be del u star z by del y, okay, and this is going to be del u star z by del z, okay. Sorry, I wrote a mistake. This is going to be, sorry, this is going to be v, that is the y directional base variable, and this is going to be w. Very sorry. But we know that these quantities are not there at all because the base flow is unidirectional, and we just have its component only in the x direction, which means that my del u star z by del x, this is equal to 0, and this is indeed true, okay. Why? Because we already know that my base flow is just a function of z, it is not a function of x, okay. This means that u star z, the capital U star z, trivially satisfies the continuity equation, okay. This is indeed true. All right, now the second equation, which is the which is the Euler's equation, if we write it down, then what do we get? So we get del u star z by del t, okay. So this is the continuity equation that we are writing, and this is the Euler's equation, okay. And then we have what? We have so yeah, so we're writing the Euler's equation, but remember we're writing this in the x direction because only we have the x directional velocity component of the base velocity. So we have this u star, which is a function of z, times del u star z by del x, okay, and this is equal to what, minus of 1 upon rho del p star by uh, del x, okay. Now we know that my base flow is steady, that we already considered it in the assumptions, which means that this term is 0. This term is 0 because your base flow is just a function of z, which now means that my base pressure del p star by del x, this is equals to 0. This means that your base pressure is not a function of x, which means, so the only possibility that I can have is that my base pressure is just some constant which is equal to p naught, okay. And this is indeed the case because in case of inviscid flows there is no mechanism which can, uh, which can balance the pressure gradient, meaning that your pressure always has to be equal to constant if I have an inviscid flow, okay. that is my base pressure. So so the the conclusion is that my base pressure is always constant, okay, in case of inviscid flows. So constant base pressure, and we will call this as P naught. So this proves that your base flow variables, so this proves that your base flow variables U star as a function of Z star and P naught, this base flow variable trivially satisfy the boundary conditions, okay. Okay. So once we know this, the next objective is to basically find out what are the governing equations that you know that that are what are the governing equations for the perturbation, that is the dash variables, okay. But before that, what we will do is we'll non-dimensionalize the variables and we'll remove the dimensionalities of the problem, okay. So the next step, that is step 2, is non-dimensionalization, okay. So we will non-dimensionalize. So step 2 is non-dimensionalization. And we have done this in numerous occasions of this course. So I hope you are just comfortable with non-dimensionalization now. Non-dimensionalization, yeah. So what we'll do is the length scale of the problem, we'll call it as h. That is the height of the channel. This is 1. The characteristic velocity scale, we'll call it as max of, let's say, u star of z star. Either you can consider it as max of this, or you can consider it as average of u star z star as a function of z star. You can consider any of this, okay, as your characteristic velocity. This means that my time scale, which is now the advection time scale, is just going to be the length scale by uc, which is just going to be h by max of u star as a function of z star, okay. This is going to be my this is going to be my time scale for the problem, okay. And then my characteristic pressure, the characteristic pressure Pc, we will call it as rho uc square, which is the advection scale for pressure, because now we don't have so recall we have two scales for pressure, the viscous scale and the advection scale. The advection scale was nothing but rho uc square, the viscous scale was mu lc by uc. But here, since we don't have viscosity, so the scale for pressure is nothing but the advection scale for pressure, and this means that my PC is rho uc square, okay. So if I now define the non-dimensional variable, so if I now define the non-dimensional variable, okay, so my non-dimensional x is going to be my dimensional x by h, my non-dimensional y, or let's write it in vector form just to skip the number of steps. So my non-dimensional x vector, which is x bar, is going to be my dimensional x vector by h. My non-dimensional time is going to be t star by tc, and we know that tc is nothing but lc by uc, so it is just going to be t star by lc by uc. And what do we have? My non-dimensional pressure p is going to be my dimensional pressure p star by pc, okay. And we know that pc is half rho infinity square, so it is just going to be p star by rho, sorry, it is rho uc square, not so half is not there, it's just rho uc square. And then what do we have? Okay, and yeah, that's it, I guess. And of course, we can also define my non-dimensional velocity as my dimensional velocity v star by uc, where we know that my uc is either max of the base flow or it's the average of the base flow, okay. So that's it. These are the non-dimensional variables that we have defined using the chosen characteristic scales. So once you define the non-dimensional variables, the governing equations now simplify. So what you need to do is, it's very simple. We have done this multiple times. Just substitute these non-dimensional variables into the dimensional equations. which are this, to get that corresponding non-dimensional equation. Okay, so you can just do that and see, that's a very trivial step. You can just do that and see that the governing equation, now if you non-dimensionalize it, they are something like this. So the continuity equation, it just gets it. So yeah, so remember, if you also need to define a non-dimensional delta, which is the gradient that we consider. So it is the dimensional delta, which is delta star, divided by the characteristic delta. So the characteristic delta happens to be 1 by LC. Okay, so that's the non-dimensional delta that we are defining. Okay, so this just happens to be del dot v equals to 0. That's the continuity equation in its non-dimensional form. And then the Euler's equation, if you just plug in the non-dimensional variables, your Euler's equation would just be your Euler equation would just be del v by del t plus v dot grad v equal to minus gradient of p. You can do this exercise at your end. So what you need to do is, I'll not do this now because we have done this repeatedly for numerous occasions. Just use this non-dimensional variable and plug this in the this dimensional governing equations to get the corresponding non-dimensional governing equation. Okay, all right. Okay, so this uh, so these are the two equations that the total aggregate non-dimensional variable would satisfy. Where I would write it down, that where your v bar, that is your non-dimensional aggregate velocity. Okay, this is a function of x and t, and this is some non-dimensional base flow variable u, that is u of z times ex plus v dash, which is a function of x bar and t, and your non-dimensional pressure, aggregate pressure, which is a function of x bar and t. This is going to be a function of your base pressure, which is, let's say, p naught bar, because you are defining your so what you can do is, you can define your p naught bar, you can define your p naught bar as your dimensional given uh, pressure, which is, let's say, p star p naught star by pc. And similarly, you can write the corresponding expression for u, which is basically u star, capital U star by uc. Okay, so this is how we have also non-dimensionalized the base flow variable. Okay, and similarly, this is p naught bar plus the perturbations, which is p dash as a function of x and t. Okay, all right. So this ends the second step of the analysis, that we have written the governing equation that the aggregate variable satisfies in its non-dimensional form. Okay, the third step, but before that, I'll stop here for a couple of minutes. I hope you have understood what we have been. We have done this very slowly, and if you have any questions, feel free to discuss. Okay. So what we did is, now we have derived the governing equations that are total aggregate variables, which comprise of the base variable and the perturbations, satisfy in its non-dimensional form. Okay. Okay. So the next step, that is the third step, is to derive linearized equation for the perturbations. Okay. See, the unknowns here, see, the knowledge of the base flow is already known. So what we need to do is, in order to know whether a given problem is stable or unstable, ultimately we need to write governing equations which govern the perturbations. Okay. So the next natural step is that once we know the aggregate equations and we know the equations that the base flow satisfies, what we will do is, from the aggregate equation, we'll try to figure out what will be the equations that the perturbation satisfies. Now, since the perturbations in general vary with space and vary with time, there, so it may so happen that the governing equations which were linear, I mean which okay, so the aggregate governing equations were non-linear, but we can see that if we substitute the perturbations here, we will see that the equations that the perturbation satisfies are also linear. But since we are in the realm of, or we are in the domain of linear stability analysis, which means that the magnitude of the perturbations are very much less than the magnitude of the base flow, what we will do is we will ignore all the nonlinear terms in the equations that the perturbations satisfy. Okay, for instance, when we'll do, things will be much more clear. Okay, so now what we'll do is we will substitute this form of, I mean, we'll substitute the fact that your aggregate variables is a sum of the base variable and the perturbations into the governing equations that the aggregate variables satisfy to derive the governing equations of the perturbations, and subsequently we will linearize these governing equations to get the linearized governing equations of the perturbations. Okay, and this we are doing, I again clarify, this we are doing because we are in the domain of linear stability analysis, where the magnitude of the perturbations are very much less than the magnitude of the base flow. Okay, all right, so what we'll do is we'll substitute, but let's name these equations first. So this is 3a and 3b. We will name this as 4a, and this is 4b, and let's say these two equations are 4c. So what we will do is we will substitute 4c into equations 4a and 4b, and and we will linearize this. Okay, and linearize, and I'll show you how do we do this linearization. Okay, so when I substitute it in the continuity equation, I just get divergence of v dash equals to 0, typically because the base flows trivially satisfy the continuity equation, and we have already established that. Okay, so this is the continuity equation that is satisfied by the perturbations. Okay, the second is the Euler's equation that we have. Okay, so what do we get if we substitute this into this equation? So the first term would be del t of what? Del t of u ex plus v dash, okay, plus u ex plus v dash dot grad of u ex plus v dash, okay, and then we have minus grad of p naught bar plus p dash. Okay, now if we commute this, what we'll get is we'll get del u ex by del t plus del v dash prime by del t plus what we will get is we'll get u ex dot grad of u ex. Okay, that's the algebra that we are doing, so we are just breaking the terms. Okay, plus v dash dot grad of u ex, where this u, remember, this capital U is nothing but the base flow profile, and then we have what we have plus plus u ex dot grad of v dash plus, then I have v dash dot grad of v dash, and then I have minus grad of p naught bar plus minus grad of p dash. Okay, now since this u, this u is just a function of z, this means that this term will just go out, and we have already considered that my base flow is steady. This means this term will not be there. This term will also go out to 0, because if I take this dot product in the x direction, I will not, and because of the fact that my u is just a function of z, I will not have any component of this term. Okay, these two terms will be there, that is fine. This term, if you take a close look at of this term, it is the unknown, that is v dash dot grad of v dash. Okay, this is a non-linear term, and since we are in the regime of, or we are in the domain of linear stability analysis, this kind of non-linear term we will discard. Okay, so I'll write it down that since so so this v dash dot c, the unknown is v dash. Okay, so these are the perturbations that we are trying to solve for. And since this is a non-linear term, that since v dash dot grad of v dash, since this is a non-linear term, we will neglect it. Since we are in the domain of linear stability analysis. Okay, all right, which means, and also this term is going to be 0 because I know that my p naught bar is just a constant, because the base pressure is just a constant. Okay, which means that the equation, that the linearized equation which satisfies the perturbations, the linearized Euler equation, boils down to the fact that del v by del t plus u ex hat dot grad of v dash plus v dash dot grad of u ex. Okay, and then I have equals to minus grad of p dash. So this coupled with the continuity equation, and also I have divergence of v dash is equals to 0. So this coupled with the continuity equation are your governing equations that are your linearized governing equations that the perturbation satisfy. Okay, so I'll write it down. So these are the linearized governing equation that the perturbed variable, which are the unknown variables, okay, the perturbed variable, which is v dash and p, satisfy. Okay, so what you can do is, so this is a vector equation, you can also write this equation in the component form, and you can verify from your end, and you can verify this from your end that in component form. Okay, in so what you can do is you can verify this at your end, and in component form, if you want to write it down, that in component form, meaning that if you want to write the equations that the perturbations satisfy, so this is the vector equation, and of course this is continuity equation, it's a scalar equation, and if you want to write this vector equation in component form, you can show that your x component is just del u prime by del t plus, because you can write this v prime as u prime ex plus v prime ey plus w prime ez. Okay, these are just nothing but the components of the perturbations that we are writing. Okay, so this is del u prime by del t plus u, which is your base variable, which is a function of z, times del u prime by del x plus w prime du by dz. Okay, and this is equal to minus del p prime by del x. This is your x momentum. Similarly, you can write your y momentum as del v prime by del t plus u, which is a function of z, of course, del v prime by del x plus, okay, this term is not going to be there, and then this is equal to minus of del p prime by del y. That's very simple. We're just not doing anything. We are just writing this equation in component form. That's all. That's all that we are doing. Okay. and this is then the z component is del w prime by del t plus u of z. Remember, this is not a nonlinear term because the base flow profile is already known to us. Okay, this is the only unknown that we don't know. So don't confuse. Don't confuse here that this is a nonlinear term. This is not a nonlinear term. This is a pure linear term because this base flow profile is already known to us. Okay, this is w prime uz of del w prime by del x, and then we have minus del p prime by del z. Okay, so these are your x, y, and z momentum equation. And then also we have the continuity. Let's not forget the continuity. So we have the continuity equation as del u prime by del x plus del v prime by del y plus del w prime by del z, and this is equals to 0. Okay, so this is your linearized equations that the perturbation satisfy in component form. I will name these equations. So these equations I'll name it as let's name this equation as 5a and 5b, and then these equations in component form, let's name it as what? Let's name it as 6a, 6b, 6c, and this is 6d. Okay. All right. I'll stop here for a couple of minutes. If you have any questions, you can ask in this context. Okay. Of course, this is the continuity equation. Okay. All right. If no questions, the next step is one of the most important steps of stability analysis. This is known as decomposing your perturbed variables into normal modes. Okay. And I think this is step what? This is step 3. So that the next step is step 4. Okay. So the step 4 is writing your perturbations in terms of normal mode. Okay. So what we will do is we will write my perturbations. For instance, I'll write my, let's say, x component of velocity, the perturbed x component of velocity, which in general is a function of x bar, and sorry, this is not this, and it is a function of time. I will write it as some u hat of z, okay, e power sigma t plus I times of kx plus ly. Okay, and I'll explain what these terms basically signify. So first and foremost, writing your perturbations as this form is known as normal mode representation. Now, why this is called normal mode representation, and how do we write this normal mode representation is governed by the physics of the problem. Okay, so where recall that this k, I think you have already seen this representation in while you are deriving the Orr-Sommerfeld equation. So remember, this k and l, these are the wave numbers. Okay, these are the wave numbers. Your sigma, this we call it as growth rate. Okay, and in stability analysis, your growth rate typically happens to be the eigenvalue, and I will justify that why this is the eigenvalue and how this turns out to be an eigenvalue problem. I'll justify that in the next in the subsequent time. But trust me that this sigma is the growth rate, that this sigma will dictate whether a given disturbance will grow with time or decay with time, and this k and l, these are the wave numbers. Okay, and and this u hat of z, okay, this u hat of z, okay, this is your eigenfunction corresponding to the eigenvalue sigma. Okay, so the representation of your perturbations into this form, this is known as your normal mode analysis. And the reason why you have chosen this normal mode analysis is that what you do is in the domain, in the domain of interest, for instance in this direction, what the the what to say, the justification of choosing normal mode in that particular form is that you walk in the three mutually perpendicular direction, and you see if there is any changes in the base flow that takes place in this direction. For instance, if I walk along x direction, I do not see a change in the base flow, so I choose normal mode in the x direction, which is reflected by the wave number L, and that's why I have, I think it is wave number K, I think, yeah. So the normal mode in the x direction, it is represented by the wave number K, and I choose normal mode in the x direction because my base flow is not changing in the y direction, in the x direction. Similarly, if I walk along the y direction, that is perpendicular to this plane, I see that my base flow is invariant, which means I can choose normal mode in the y direction, which is reflected by the wave number k. So that's the reason why I have considered it as I times of kx plus ly. Okay, because I can choose normal modes in that particular direction. Okay, but if I move along the z direction, I see that there is a change in base flow that is taking place in the z direction. That means I cannot choose a normal mode is in the z direction. That's the idea. Okay, so it's like it's so the idea is again very similar to the to the fact that you can represent, it's very similar to the fact that you can represent any arbitrary function as as sines and cosines, and if you take your domain to be going from plus infinity to minus infinity, this happens to be a Fourier transform. So this normal modes that you consider, this is nothing but the result of the Fourier transform only. Okay, because your x is varying from plus infinity to minus infinity, your y is varying from plus infinity to minus infinity only. And so it's kind of a consequence of the Fourier transform that you choose the normal modes in that fashion. So recall that your k and l, these are generic wave number, and if you want to write an integral, you are basically actually doing an integral from plus infinity to minus infinity dk, and plus infinity, or in fact minus infinity to plus infinity dl. You are essentially, so the idea is that you are essentially integrating, you are representing a perturbations in a Fourier space where you are integrating the wave numbers from minus infinity to plus infinity, and this integration you are representing as a generic wave number k and l, and this is actually the essence behind this normal mode analysis, and this is essentially the math behind this normal mode analysis. Okay, so we don't, so please try to realize that there is an, there is a, what to say, there is actually an integral that is taking place over this form with respect to dk and dl, and what we are doing is we are representing this integral in terms of any generic wave numbers k and l, because of the fact that individual wave numbers do not, they do not interact with each other. Since the individual wave numbers do not, and this is again a hallmark of normal mode analysis. Okay, since the individual wave numbers do not interact with each other, or the individual modes do not interact with each other, I can represent all the modes in normal mode analysis as a generic mode k and l. And this is again a similar thing that, remember, we did this when we solve the eigenfunction problem of e4 psi equal to 0, if you remember. Okay, what we said is that any function in a space, I can always represent this as summation of modes. Now if it's a discrete space, it becomes Fourier, it becomes Fourier series if it's a discrete space. If your space varies from plus infinity to minus infinity, you have all the modes that are present, and then the series basically transforms to an integral, and that becomes the Fourier transform. Okay, so this analysis of normal mode comes from this Fourier transform, because now since my domain varies from, domain in x and y varies from plus infinity to minus infinity in both x and y direction, meaning that all the individual modes will be present, and since the individual modes does not interact with one another, this means that I can discard the integral taking place from minus infinity to plus infinity over dk and dl into just two generic variables k and l. And the essence is that the individual modes, that is the individual K1, K2, K3s, the individual L1, L2, L3s does not interact with one another. And that's the actual essence of choosing normal mode of this form. I hope you have understood. I did not explain it in details because I hope you have understood this in the theory classes. But please, spend some time in trying to understand how did we get into this form of the normal mode, and what does these wave numbers essentially signify, and why did I say, what did I mean when I say that there is a invisible summation, invisible integration taking place over dks and dls basically. Okay, and how did we this and why did we discard this summation, and why basically we wrote this or why did we discard this integration and wrote this in terms of knl, and this representation is essentially known as the normal mode analysis. Okay. All right, so this is the I hope you have understood this. This is the x, so this is representing the x perturbations. Now we'll represent the y perturbations, for instance v dash, which is a function of x and t. This is going to be v hat of z. That is the similar representation. It is going to be e power sigma t plus ikx plus ly. Okay. And similarly, I will write my w prime as x and t as w hat of z times e power sigma t plus I kx plus ly, and I can also represent my pressure as p hat of z e power sigma t plus I kx plus ly. Okay, so this is the normal mode representation that I was talking about. Okay, so let's name this equation. This is 7a, this is 7b, this is 7c, and this is 7d. All right. Okay. Okay. I hope now you are clear on how did we write the perturbed quantities, for instance, the three velocity components of the perturbations and pressure in terms of the normal modes, having wave numbers k and l and eigenvalue sigma with an eigenfunction, the head variables. Okay. All right. Okay. So we'll do one more step before calling it a day today, and then we'll proceed it in the next class. So what we'll do is we'll do a transformation. So so this is typically done in the books, and that's why we will do. So we'll do a transformation here now. What we will do is we'll consider this sigma as minus I times alpha times c, and this alpha is nothing but equal to k, which is just the wave number, and we'll call another variable beta, another transform variable beta, which is just l. So this c is now my eigenvalue. Okay, and your k becomes equal to alpha and your l becomes equal to beta. That's it. So what I can now do is, if my c is my eigenvalue, remember my eigenvalue can be real, my eigenvalue can be imaginary, or it can be both real and imaginary. So in general, I can write that my c is some real part of CR plus I times the imaginary part of CR, because eigenvalues can be anything, right? They can be real, they can be imaginary, or they can be a mixture of real and imaginary parts. Okay. Which means that if I simplify this term, if c the only thing, if you have a closed loop, the only thing that dictates if these perturbations will grow or decay with time is this term e power sigma t, because this is a periodic term. Okay, this will not hamper, so this will just have a periodic nature. The only term, I repeat, will dictate, okay, when, so as to where these perturbations, so as to when these perturbations will grow with time or decay with time, is this e power sigma t. You can appreciate that if sigma is less than 0, this term is negative. This means that my perturbations will come down or decay. If my sigma is greater than 0, this term will blow up. That means at time t equal to a very large time, this term will eventually dominate, and then my perturbations will just grow it will exponentially grow with time. Okay. So taking this motivation, I can say that if I evaluate this term e power sigma t, because this is that term which dictates the growth rate. And then if I write this sigma in terms of this new transform variable c, which is my eigenvalue, it becomes minus of I alpha c times t, and then I can write this as minus of I alpha. C can be written as cr plus I times of ci, and then there is this time, which means I can write this term as minus, okay, I can write this term as minus I alpha crt, and I have plus alpha ci, okay, t, and then I can write this as e power alpha cit, okay, minus or I can write it as e power minus I alpha crt. Okay, so whether my perturbations will grow or decay will be dictated by this term, because this term is, because this has an I in it, which means this will be periodic. This means that my growth or my decay will be dictated by, so if I have a growth, this means that alpha ci has to be greater than 0, meaning that my ci has to be greater than 0. If I have a decay, this means that alpha ci has to be less than 0, meaning that my ci has to be less than 0, because your wave numbers are just a positive number. Okay, so this is the condition for that you get, which assess the stability of the problem, meaning that you calculate your eigenvalue. If your imaginary part is less than 0, this means the perturbations will decay with time. You calculate your eigenvalue, and if your imaginary part is greater than 0, your perturbations will grow with time. Okay, so if ci is greater than 0, perturbations will grow with time, and if your ci is less than 0, your perturbations will decay with time. Okay, so the condition for stability is that ci less than 0. So in other words, you can say that this is the condition for stability. I think there is a miss. I think my internet connection has just, okay, I think it's back. Yeah, sorry, I think it's back. Yeah, so this is the condition. So what I was saying, that this is the condition for stability, that is your imaginary part of your eigenvalue is less than 0, and this is the condition for instability. Okay, all right, so what we did is, we'll carry the math in the next class, but let's have a quick recap, because it involves some extensive algebra. What we did is, we started off from the problem statement. We defined the base properties. We said that the magnitude of the perturbations will be less than the magnitude of the base flows to stay in the domain of linear stability analysis. And then we wrote the governing equations for the aggregate variable dimensionally. Okay, and then we said that the aggregate variables can be written as a sum of the base variables plus the perturbations. And then we non-dimensionalize. Okay, we also saw that the base variables trivially satisfies the governing equations, meaning that we choose some non-dimensional scales, the characteristic scales, to first non-dimensionalize the given equations that the aggregate variable satisfies, to basically get the non-dimensional equations, which is given by equations 4a and 4b. And then what we did is, we substituted the fact that you can write the aggregate variables as sum of the base variables and the perturbations into the governing equations, to get linearized equations for perturbations by discarding the non-linear terms. And once we get linearized equation for perturbations, for instance equations 5a and 5b written in component form as equation 6a, 6b, 6c and 6d, what we do is, that's the most important step, we carry out the normal mode analysis, meaning that you can write the perturbation in terms of the normal modes. And as I said, the idea of this, so how do we choose a normal mode? Walk in direction of the base flow. If the base flow does not change, you choose a normal mode in that particular direction. If the base flow changes, you cannot choose a normal mode. Okay? And the essence of these normal modes is denoted by the wave numbers k and l, where since your domain varies from minus infinity to infinity, there is an invincible integration taking place over this wave number. But since the individual modes or the individual wave number does not interact with each other, I can represent all the wave number as a generic wave number k and l, because I have two dimensions here. Okay, that's the essence of this normal mode analysis, where this sigma happens to be the growth rate, which is the eigenvalue of our problem, and the corresponding eigenfunction is u hat of z. Okay, and then what we did is we represent all the variables in this form, and then we use a transformation where the original eigenvalue sigma is now represented as a new eigenvalue c with a prefactor I alpha. That's the thing, where this alpha was the wave number associated with k and beta is the wave number associated with l. And that we then the condition for stability is that the real part, the imaginary part of the eigenvalue c has to be greater than 0. Sorry, that's the condition for instability. Okay, and if the imaginary part of c is less than 0, that's the condition for stability. Okay, that is simply boils down to the fact that I just need to assess whether this term e power alpha cit, will it grow with time or will it decay with time. Okay, if it grows with time, that's the condition for instability. If it decays with time, that's the condition for stability. Okay, so in the next class, what we'll do is we will insert these normal modes that we derive. We will insert this normal mode that we derive into the governing equations that this perturbation satisfy. And then what we'll see is we will use a very powerful theorem. Although we may not have time to actually prove this theorem, we'll use a very powerful theorem which is known as the squares theorem. It says that for a given base flow and for a given wave and for the same wave number, that is for a given and the same wave number, 2D disturbances are stronger than 3D disturbances. Okay, this is what squares theorem says, and this is a very powerful theorem because we will use squares theorem and discard one of the given direction, that is we'll discard one of the variables, and then instead of having 4 unknown variables, we'll just have 2 unknown variables in the velocity and then pressure. And then since then my problem becomes a 2D problem, uh, courtesy of the squares theorem, we can use something which is known as the stream function, which we have already been doing. And then we will also use the normal mode in the stream function to basically finally get the Rayleigh stability equation, which dictates how the disturbances eventually grow with time or decay with time. Okay, that's the roadmap that we will do it in the next class. But I hope you have enjoyed stability analysis and you have enjoyed the physics behind the stability analysis at least up to this point of time. Please let me know if you have any doubts. You can post it in the discussion forum, or else we'll meet in the next week at the same time using the same link from 3 to 5. Okay, thank you very much. And if you have any questions, as I said, please feel free to post it in the discussion forum and we will be happy to address this. Okay, and just couple of things. So next class is the last formal class that we'll have, but I think we will have one more extra class basically to finish up the things that I was planning to say. And after that you will have your exams, and I think you are clarified that your exam pattern is going to be similar to the pattern of questions that you see in your assignments. Yeah, I think that had already been clarified in the discussion forum, but I wanted to address this here as well. Okay, so thank you for watching these videos, and I hope you are enjoying learning this course. Keep enjoying and keep learning. Thank you very much.